Hello everyone, and welcome back to the channel Airbus What's It Doing Now, and to this episode of another Airbus Safety Magazine article concerning the prompt response, or the importance of a prompt response to a engine fire warning. The idea behind this is to help keep the fire under control by a prompt response and to keep the situation manageable or prevent a deteriorating situation. We're going to take a look at a case study, and the probable cause of this particular case study was they believed to be a hydraulic leak, which was the potential damage to a green hydraulic line whilst the engine was under maintenance. So that would they believe the most probable cause of this particular event. As always with these videos, this isn't about pointing the finger on the what's and what they should have done, etc. And we're very fortunate to have access to this information because as pilots we're always learning, aren't we? And having access to this information means that we can learn from other events, because it's not always about what we do right, but sometimes when we don't do something right we can all learn something from it. So some of the other things we're going to take a look at is the probable distractions, the problem solving and decision making, and some of the indications the crew actually had during this engine fire, which is quite interesting, particularly as they saw normal engine indications when what they would have likely have seen during this event, such as the M1s, N2s and EGTs initially, and the fact that the fire likely restarted because of the delay in responding to the ECAM. We'll have a look at a reminder of the fire detection and suppression systems on board the aircraft as well, which is a really good review, and a reminder of the types of fire, such as the nacelle fire, which is like if you like around the engine, and the tailpipe fire, and how we deal with both of them, because of course they're very different. I've got some videos in here as well which I'll put up, as well as some illustrations. Before we get into the article, I thought it would be a good idea to have a quick review of some of the tech and what happens when we press the fire push button on the overhead panel. Now, I've covered this as part of fire detection and suppression, and I'll put a link up here somewhere so that if you haven't seen that already, you can go ahead and watch that, or you might want to look at it as a bit of a review before getting stuck into this. So to begin with, we'll have a look at the engine 1, 2 fire push button. I've pulled this straight out of the FCOM, so a good time to review. So the push button normal position is obviously in, and it's flush obviously with the guard cover over the top. When the flight crew pushes it, the push button is released under that sort of spring pressure and sends an electrical signal that forms the following performs the following for the corresponding engine. First of all, it silences the fire warning if the crew haven't already pushed the warning annunciator. It arms the fire extinguisher squibs. Now, when we discharge, you get the discharge light come up, but that's when the bottles have lost the pressure. So this is a little reminder here that you won't necessarily see the discharge as soon as you press the push button, but comes on some while after, when the extinguisher has left the bottle and the pressure decreases below a certain amount. That's when you'll see the discharge. Closes the low pressure fuel valve. It's an interesting one, that, of course, because with some electrical failure cases, you need to use the QRH to shut the engine down, to actually push and request that you push that overhead fire push button to shut the engine down. That's a QRH procedure. So a reminder, it closes the low pressure fuel valve. It closes the hydraulic fire shut-off valve as well, which is critical in this particular scenario that we're going to take a look at. It closes the engine bleed valve, and it also closes the pack control valve, which is why it's really important to prevent any contamination to close the cross bleed. And it's an expanded procedure in the FCOM whenever you press the fire push button. We covered that also. It cuts off the phatic power supply, obviously, and it also deactivates the IDG. The red light comes on regardless of the push button position whenever the fire warning for the corresponding engine is activated. So when you push the button and you extinguish, say, both the squibs, the fire light will stay on if a fire is detected by those fire loops, of course, which are those heat resistant or conducting wires, basically, which give you the fire detection. And what happens actually when they fail, as we take a look in this particular case study. Right, so the article then, let's get stuck into it then. So Safety Magazine covers this article, and it's something I do on the channel as often as I can, or if I see something that's I think is worth reviewing. And I thought this was quite a nice one to do, because we obviously cover it as part of recurrent SIMs, and sometimes an rejected takeoff and evacuation is required, or an airborne shutdown with damage, or fire. So having a look at some of the tech behind it is probably a good review, and in this particular case study as well, the importance of getting on with it, really, as we will see. So several recent engine fire events highlighted the importance of a timely application of the engine fire procedure. This article explains why flight crew must apply this procedure without delay. Decisive action when there is an engine fire alert may prevent further damage to the engine. Now, we're not talking about reusing the engine later on, but we're talking about substantial damage to the engine that causes us more problems. This can help to ensure that a manageable fire situation does not become an uncontrolled fire with more serious consequence. Remember, when we push that fire push button, it cuts off all of those ancillary controls such as electrical or hydraulic services and bleed, etc. So it's really important to move on with that as quickly as we can. So this case study concerns an A330. It doesn't really matter. It has the very similar makeup in terms of the procedure, and the message is exactly the same on all of across the aircraft types. There might be a few peculiarities with some of the ECAM, which it talks about later on, but for all intents and purposes, it's the same message. So an A330 aircraft departed for a long-range flight, and the aircraft was in config 2 for takeoff, and takeoff roll was normal, but the engine 2 fire red ECAM alert was triggered at 17 seconds after takeoff. The flight crew continued the climb, and the engine display showed stable engine parameters for both engines. I think that's the first thing that may have been part of the reason the crew may have delayed it. It doesn't say that here, but it does allude to that a little bit later on in the report. But an important thing to take away. At takeoff plus 51 seconds, the aircraft reached 2,400 feet radio altitude. The pilot flying set engine 2 thrust lever to idle and pushed the engine 1 thrust lever to toga. So that's 51 seconds before the thrust lever came to idle. 52 seconds, so a second later after going to toga, the pilot flying sets engine number 1 thrust lever to MCT, and this caused the auto thrust to engage in thrust mode, which would be thrust MCT. So that was at 52 seconds after. At 2 minutes and 27 seconds, the flight crew sets engine master 2 lever to off, so they're obviously going through the ECAM at this point. And 2 minutes and 43 seconds, the flight crew pressed the engine fire push button and discharged agent 1, followed by agent 2. The engine fire alert remained after both agents were discharged. So the aircraft at this point is still on fire. At takeoff 3 minutes and 38 seconds, the flight crew engaged the autopilot and levelled off the aircraft at 7,000 feet. So some while later, almost a minute later for the level off. So at 6 minutes and 31 seconds, the flight crew started the APU, which provided an electrical power supply to the right side of the aircraft. This leads me to believe they're going through the ECAM systems pages now and starting the APU. This is now going to power AC bus 2 because generator 2 isn't available on that side. At takeoff 9 minutes and 39 seconds, the EGT indication for engine 2 started to increase, even though it had shown a decreasing EGT from when the time the engine 2 master lever was set to off. This is believed in the report that the fire may have likely reignited. Okay, I'll come on to more about it later on, but now we've got an EGT increase after the crew saw it reduce, as you would expect to see after you shut the engine down. At 10 minutes and 3 seconds, the engine 2 fire alert stopped and the engine 2 fire detection fault amber ECAM alert triggered. Excuse me. This is because the fire loops are now damaged. So the fire is, I guess, that intense that it's now damaged the fire loops, so it can't give you the fire warning, and the fire detection fault is now illuminated. The aircraft engine is still on fire at this point. Excuse me. At 11 minutes and 23 seconds, the engine 2 EGT over limit amber ECAM alert is triggered when the engine 2 EGT reaches 600 degrees. So the fire is now spreading to the back of the engine. At 15 minutes and 9 seconds, the engine 2 N1 value became invalid. That was due to some damaged wiring. There's not an awful lot more the crew can do at this point. They fired both bottles after having pressed the fire switch, but a lot of this is due to arguably the delay in actually carrying out that procedure. So at 25 minutes and 2 seconds, the aircraft touched down the runway safely, came to a stop. Smoke and flames coming from engine 2 were seen. The fire brigade arrived and extinguished the fire. So still on fire 24 minutes after the initial warning. So yeah, that's quite staggering really, isn't it? So it then talks about the event analysis and probable cause identified, and I've talked about this slightly earlier on, but I'll read through it because it makes for a good read. The investigation enabled Airbus to conclude that the most probable cause of the engine fire was a leak from the green hydraulic circuit, which may have been due to damage on the green hydraulic line during maintenance. So I guess what's happening is hydraulic fluid is leaking out of this circuit, which ultimately there was enough of it and reached a certain temperature, the flash point of the hydraulic fluid, it then caught fire. Delayed application of the fire procedure. Any red ECAM alert requires immediate action by the flight crew to ensure that the continued safety of the flight. When the engine 2 fire alert is triggered and red land ASAP memo appears on the ECAM, this requires the flight crew to land as soon as possible at the nearest suitable aerodrome where a safe landing can be made. And that's exactly how it's written and how to respond to a red ECAM. During this event, the engine 2 thrust lever was not at idle until 51 seconds after the engine 2 fire alert was triggered, so it's still at sort of takeoff thrust or climb thrust. A further 1 minute and 36 seconds passed, that's takeoff 2 minutes 27, before the engine fire procedure was completed to isolate the fire and use the extinguishing system. Normal engine parameter despite the fire. The engine indications in the cockpit appeared to show that engine 2 operation was normal. This may have been a factor in the flight crew's decision to delay the application of the fire procedure. So it's interesting that, isn't it? Because when you've got a fire light on the overhead, it's fairly conclusive. But of course, if you've got normal N1s, normal EGTs, normal N2, I don't know, maybe there's a question mark in the crew's mind as to whether or not the engine was damaged or run down. But in any case, getting on with the thrust idle and the master off would arguably have been, might have happened earlier. Remaining fire and further propagation. So the analysis showed that the engine fire extinguishing system operated as intended and both extinguisher bottles correctly discharged during the event. It's likely that the fire reignited shortly after extinction due to the remaining conditions of the fire reignition in the nacelle. So the remaining conditions would be oxygen, we still have tick, heat, we definitely have tick, and fuel, tick, which is obviously the hydraulic fluid. So we have three elements of the fire triangle there, I guess, still present, and that's likely why it would have reignited. Remember, the crew did push the fire push button, of course, but my guess here is, and what they're alluding to, is a sufficient amount of it caused, or the delay in it caused sufficient amount of it to gather in order for it to reignite. The EGT increased up to 801 degrees, which is a sign that the fire spread towards the EGT thermocouples. The fire continued to cause destruction for the engine, fire detection loops and damage to wiring. This is the reason the engine 2 fire ECAM alert stopped and was replaced by the engine 2 fire detection amber alert. Note that this alert was in the overflow part of the warning display, indicated by a green arrow. You remember that on the ECAM, if there are more items, you then have to clear it in order to get to the bottom. Similarly, the loss of the N1 information was due to damaged wiring. So quite a lot going on there, really. Obviously due to the delay in actually actioning the ECAM led to a worsening situation where actually they weren't able to control the fire, despite 2 fire bottles been applied. So the key message there is to apply it in a timely fashion. It's a red ECAM and obviously a red land ASAP. Two types of engine fire. There are two types of engine fire. I've got the illustrations up here for you, which is the engine fire, which is commonly known as a nacelle fire, and a tailpipe fire or internal fire. Both types of fire affect the engine but are treated differently. Obviously, one you have fire suppression for, which is the nacelle, and the tailpipe fire we don't have suppression for, but we obviously have a procedure for, and I have some videos up here as well while I'm talking, which I'll bring up to show you a couple of engine tailpipe fires during engine starts. I think one was a 7.3 and the other one was a 1.46. I couldn't find anything on a 320, but I'm sure if you dig around you can probably find something. So the engine fire, nacelle fire. An engine's fire affects the external part of the engine core, so around the engine core, but it's contained within the engine nacelle, the bit that we can see. This type of fire can occur on the ground or in flight and is usually caused by a malfunction or rupture of a component or pipe which contains flammable fluids, e.g. fuel, oil, hydraulic fluid, etc. When these fluids come into contact with the hot surfaces of the engine case, such as a high pressure compressor, combustor or turbine, they can self-ignite and cause a fire. This was the case in this particular example. This type of fire can also be caused by a rupture of part of the engine core, causing damage to components, pipes, which can also lead to a fire. So if it starts spitting guide vanes or compressor or turbine blades, etc., that penetrate through the core out to the nacelle, then of course that could also cause a rupturing of these critical components. The fire protection system will detect a fire and trigger the red engine 1-2 fire ECAM alert. The flight crew must apply the associated engine fire procedure without delay. The tailpipe internal fire, as it's called, a tailpipe fire occurs inside the engine core. This type of fire will only occur during engine start or during the shutdown sequence. It's usually because of oil or excess fuel in the combustion chamber, or on a subsequent engine start after a failed start if there's any fuel left over. A tailpipe occurs when the engine rotates at very low RPM and residual fire is present in the combustion chamber, or in the turbine area, or if there is an oil leak of some sort in the tailpipe of the engine. The risk of tailpipe fire is higher in the case of a second engine start attempt because of residual fuel which will remain after the first engine is started. I said that earlier on, didn't I? So I'm repeating myself now. The fire detection system does not detect tailpipe fires because they occur inside the hot sections of the engine core where there's meant to be a fire. And therefore are outside of the fire detection zone. I'll show you on some illustrations here where those zones are. Flight crews can detect tailpipe fires by observing any abnormal increase in the EGT during an engine start, or if the EGT does not decrease after shutdown. Ground crew, cabin crew or air traffic controllers may also observe a tailpipe fire and must inform the flight crew. I dare say the passengers will probably see it as well. In the case of a tailpipe fire, the flight crew must apply the engine tailpipe fire abnormal procedure from the QRH, which basically involves venting and dry running the engine. This will ventilate the engine, the airflow will extinguish the fire and remove any residual fuel or vapour from the engine. Talks about the 220, but I'm not going to talk about that. After the tailpipe fire inspection by maintenance is required to check that there is no flame damage to the flaps, wing or pylon areas. Well, one of the videos I had on here, there was a lot of fire, so I imagine that would almost certainly have required some investigation. So rely on the engine fire alert. The detection system for engine fire is composed of dual sensing element loops. I'll see if I've got a photograph of them here, because I picked up a photograph at some point, but they're basically two metal wires basically that are sort of held in place by brackets going around the engine. That's all they are, loop A and loop B. They are located around the areas of the engine with the highest risk of fire, near compartment or air exhaust or for overheat detection. There are zones where flammable liquids are present with a potential ignition source, such as accessory gearbox area, the pylon area above the combustion chamber area and the fan area on certain engines. Each loop is doubled, that's loop A or B for redundancy purposes, and the loops can detect fire or hot air leaks. There are procedures if you're dispatching without one of the loops operative in the MEL, in which case then one loop then from memory will give you a fire warning if it detects it. The dual sensing element loops are monitored by the FDU, which is the fire detection unit. Again, I cover all this in fire protection. The fire protection function hosted in 350 aircraft, or the fire detection and extinguishing FIDEX on the 220. Anyway, for us it's the FDU for the 320. The design and redundancy of the protection loops ensure a high level of reliability for the engine fire detection system. In the event of an engine fire alert, the flight crew must rely on it. It's robust enough to give you a warning, and it must be followed. And it must be followed in a timely fashion. Engine parameters may remain normal during an engine fire. Flight crews must be aware that the engine thrust and engine parameters can remain normal in the early stages of an engine fire. The event described in this article is illustrative of that fact. So if you've got a flammable fluid within the nacelle part of the engine, then it's not affecting the N1, the N2s or the EGTs at this point. So essentially it's going to look normal. As is in this case with this hydraulic leak, it caught fire, engine's quite happy in terms of its ability to produce thrust. Of course, later on when it reached the hot parts of the engine, the EGT then started to increase. So key points, in the event of an engine fire alert, the flight crew must apply the procedure even if the engine thrust is stable and the engine parameters are normal on the engine display and on the SD page. You've got a big fire light over your head, which is a big clue, but you might not see the other characteristic engine damage parameters. And I know this is something that we practice in the simulator, and whenever we do, often we do damage, don't we, really, and we're looking for M1s and N2s. What they're saying here in this case with these sorts of fires, that the engine will look like it's behaving normally. So apply the engine fire procedure without delay. The architecture of the nacelle is designed to contain a fire threat for a minimum but also a limited time. So by design it has to contain that fire, but it won't contain it indefinitely. Therefore the flight crew must apply the engine fire procedure without delay when there is an engine fire alert. Timely application of the engine fire procedure will limit the fire propagation and prevent further damage to components or pipes around the engine core. Such damage could cause additional leaks of flammable fluids, which could increase the intensity or duration of the fire. So the point here is, the earlier you deal with it, then the less likely you are to have subsequent problems, and the more likely you are to have successful control over it in the early stages than not having control of it as the situation then deteriorates. So quick prompt action is a greater assurance of dealing with the problem and restricting it and having a manageable situation. Best practice, the use of the autopilot in the case of an engine fire alert reduces crew workload and enables a safe handling of thrust asymmetry that is induced when the thrust is reduced on the affected engine. Yes, of course, it's all part of workload management, isn't it? Therefore, the flight crew can apply the ECAM procedure earlier and under less stress. In this case, the autopilot was selected at 7,000 feet, so quite a long way after the flight, the warning occurred. So yeah, perhaps earlier application of the or earlier selection of the autopilot would have reduced the workload, and they might have had a better picture of the situation, or may have been able to work through it a little bit more quickly. Detection fault and fire propagation. The event described in this article shows how fire can propagate and damage the fire protection loops, which cause the engine fire warning to stop and be replaced by a fire detection amber fault. As a precaution, the flight crew should interpret a replacement of the engine 1 or 2 fire red alert by an engine 1 or 2 fire detection fault amber alert as a sign of potential propagating fire. So the steps of the engine fire procedure. Step 1 is the shutdown. The first step of the engine fire procedure is to set the thrust lever of the affected engine to idle and set its master switch to off. This will cut the fuel supply off to the affected engine by closing the HP and LP valves. Second stage is isolation. The second step is to press the fire push button for the affected engine in order to completely isolate the engine from fuel, electrical, hydraulic and pneumatic systems. This is to prevent further damage or fire propagation and prevent smoke from entering the air conditioning system. I think that's the important bit there to take away here, or one of the important factors. Step 3, fire extinguishing. The third step is to extinguish the fire by discharging the fire agents into the nacelle one after the other when in flight, or it says simultaneously when on the ground. This was interesting actually. I hadn't realised this, that the 10-second delay requested by the ECAM procedure to discharge the agent 1 in flight enables N1 to decrease. This will reduce ventilation of the nacelle so that the fire extinguishing agent is more effective. For some reason here, guys, the audio stopped on the video, but no problems. We're just coming towards the close here in any case. So just putting up the last key point here, which states that the flight crew must complete the procedure and discharge the agents as long as the engine fire alert is displayed and the fire lights are still on the overhead panel and on the pedestal. So a reminder there that even if the engine indications appear normal, the fire light on the overhead and on the engine pedestal should be conclusive. Aircraft engines are equipped with a reliable fire detection system. Flight crews must be aware that in the event of an engine fire alert, the engine parameters can remain normal in the early stage of the fire. Therefore, the flight crew must apply the ECAM procedure without delay, even if the engine display and engine SD page display normal parameters. Timely application of the engine fire procedure limits propagation of the fire and prevents further damage to the components or pipes around the engine core that may create additional leaks of flammable fluids and increase the intensity or duration of the fire. The flight crew must complete the engine fire procedure and discharge the agents as long as the engine fire alert is displayed and the fire lights are still on the overhead panel and pedestal. By taking decisive action when there is an engine fire alert, the flight crew can prevent a manageable fire situation from becoming an uncontrollable fire with more serious consequences. That, ladies and gentlemen, concludes this episode on the Airbus Flight Safety Corner and the Do Not Wait to Apply the Engine Fire Procedure article. Hope you've enjoyed it. Thanks very much for watching. Keep the plate spinning, stay safe, and I look forward to seeing you on another episode in the near future. Thanks very much and take care.